Today we are very happy to have Dr. Andreas Baumgartner from CU. And Andreas received his PhD from the University of Canterbury, New Zealand, 2006. Work there was on radar measurement of mesosphere winds in Antarctic region. And after that, he went back to Germany to work in Max Planck Institute for Chemistry as a postdoc. And then he served as a project manager in German Aerospace Center, DLR. And currently he's a research associate at CU Aerospace Engineering Department. And he's working on the Global Electric Circuit project, which is going to tell us more today.
Thanks very much, Henley. And thanks for the invitation to speak here. I will be talking about the exciting field of the global electric circuit. And that's a very diverse research field. I myself mostly work on the conductivity of the troposphere and stratosphere. And while HAO has several connections to the global electric circuit field, the stratosphere-troposphere conductivity is probably not the main aspect of HAO connections. So I thought I'd spend half of the time of this talk to talk about a little bit about the history and motivations for studying the global electric circuit. Then the second half, I'll talk about conductivity and how that translates into potentials and currents using GEC models for three different sort of scientific scenarios: a solar cycle influence on the global electric circuit, volcano influence, and the role of non-electrified clouds. But let me start with telling you what I'm not going to talk about. I'm not going to talk about the exciting stuff, the blue jets, red sprites, and elves. That's all stuff that happens on a very short time scale. And I'm going to talk about time scales that are longer than that, longer than about a second or so. Generally, the atmospheric electricity work is sort of divided into electromagnetics, AC field, and DC electrostatics. I'm only going to talk about DC. So this is a sort of very overview picture of the global electric circuit from a paper in Physics Today. The energy source for everything that's happening in here is basically solar heat that creates convective updraft and thunderstorms, and at the end provides positive charge sort of at the tropopause level and a negative charge mostly below. That's at least a sort of average case that's happening. And because of the potential differences, then you get currents flowing up to the ionosphere called Wilson currents. Got him a Nobel Prize for finding that out. And they then distribute around the rest of the globe. And because of the potential difference between the ionosphere and the ground, there's a small current going downwards. And that is slightly changed by different features of the atmosphere, so aerosols, clouds, for example. To give you a few numbers, there's sort of the same picture, just with numbers to what's happening. So with about 40 flashes or so per second, the thunderstorms overall generate 1 to 2,000 amperes that charge the ionosphere to about 250,000 volts. And that potential difference then drives this fair weather current in the region where there's no thunderstorms of about 2 to 3 picoamperes per square meter. The total resistance that goes through, so the total resistance of the entire atmosphere is about 200 ohms. You can also look at the system as two capacitor plates and say this is a capacitor with about 1 farad and a time constant of a few minutes. So if you would turn off all the thunderstorms, within a few minutes your ionospheric potential would be would disappear. And he wasn't actually trying to prove that the air is conductive, because generally people thought, well, it's only lightning strikes that can make electricity go through air in some form. He was actually rather annoyed because all his experiments didn't work out as well as he thought, and that was because the air is conductive. But still, he can be credited for finding out that even atmospheric air without any lightning is actually conductive. And I'll be talking about how conductive it is in the sort of sciencey part of the talk later on. And it was pretty quiet for a while. In 1859, the big next milestone happened. Lord Kelvin managed to measure the positive potential gradient of the air. And that was actually quite surprising that there was something happening at all, because people thought, well, when there's a thunderstorm, you have an electric field. But when there's nothing happening, then you shouldn't get any electric fields in the atmosphere. And it is also very tricky to measure that, because everything is much more conductive than air, including your instrument. So if you have any objects around, you're going to destroy your electric fields that you get. And this is one of Lord Kelvin's electrometers here. But he managed to perform that measurement and got a gradient of 137 volts per meter, which is actually really close to what it should be. So it's quite amazing, really. The ionosphere, or the highly conduction, or the high conductivity of the upper atmosphere, so it's sort of the discovery of the ionosphere, was then found in 1895 by these three gentlemen. In terms of lower atmosphere electricity, Hess and Bergwitz were the next two big names there, because they discovered that not only radon or radioactive decay in the lower atmosphere ionizes the lower atmosphere, but also cosmic rays ionize the atmosphere at higher altitudes. Unfortunately, the Nobel Prize only went to Hess, but Bergwitz was actually the first one who noticed that. He got his friends to, who in the ballooning club to install an ionization measurement, and he just wanted to see how the ionization rate decays with height, because that's what people thought should be happening. But instead, he found a decay, but then an increase again. And then people thought, well, that must be his instrument that is wrong. His colleague told him, don't you dare publish that, otherwise you'll ruin your academic career. He did, however, give the data to Hess, who then later on proved that this is actually true, and that must be due to some cosmic rays coming from outer space. This was a very exciting time for scientists. He actually got to fly on balloons for other types of measurements as well. This guy is Wiegand, who's measuring conductivity, the function of height here. And they did lots of flights in the sort of those 10 years here. But the big sort of next milestone was by E.T.R. Wilson, who put all the information that they had gotten by then together and showed that, or suggested that the continual atmospheric ionization from thunderstorms charges the upper atmosphere, and then that returns via a small vertical current density in regions where there are no thunderstorms. Got him a Nobel Prize for that suggestion. To further look at that and prove that this concept is true, scientists on the Carnegie vessel came up with the Carnegie curve through lots of measurements of the potential gradient during 10 years, or actually 20 years, and 500,000 kilometers that they traveled on sea with this boat here. It's actually made entirely from wood because, as I said, any objects, especially any metal objects that are conductive, will make your electricity measurements of all kinds very tricky. And
this video presents Poisson's equation and Laplace's equation for electrostatic fields. Okay, so here's an example of a problem that we would like to solve. We have a volumetric charge density contained within a volume V, and the volumetric charge density is rho sub V as usual. And at some point P, we are interested in finding some field quantity, such as the voltage at point P or the electric field at point P. So from what we've just seen, we know that Laplace's equation applies, and if we can solve this equation, given this volumetric charge density, rho sub v, we can find v, and from v we know that we can then find E by going backwards. So this is a challenging problem to solve, or more challenging to solve, because it is again a non-homogeneous differential equation. And it would be easier to solve if the right-hand side were 0. In fact, the right-hand side is 0 in many parts of this problem. If I take this field point, or this observation point, and I move it outside V, so let's say I move it outside of this volume to this point shown here, then actually at that point, there is no volumetric charge density. So the right-hand side is 0, and we get the homogeneous equation that we're looking for. So that equation, where the right-hand side is 0, is called Laplace's equation. So it is a special case of Poisson's equation, and it holds everywhere outside the source region. So everywhere outside this volume V, our problem reduces to solving this homogeneous differential equation, and it basically turns into a boundary value problem. It's important to also realize that we can apply the same concept to many other charge distributions, not just volumetric charge distributions. So the same is true in turning Poisson's equation into Laplace's equation if we had a surface charge density, or a line charge density, or even a discrete distribution of point charges, so long as our observation is not coincident with the charge density itself or the point charges in the case of a discrete distribution, we can turn the problem into solving Laplace's equation. And even with a combination of volumetric, surface, line, and discrete charge distributions, we can apply the same concept.
Here we have two conductors and a voltage source attached to them, and we want to find the electric field intensity and the electric potential field everywhere. We have used a variety of techniques to find the electric field intensity. One of them was from Coulomb's law. So if we have some differential charge element, such as a rho sub s ds here from a surface charge, the contribution of the electric field intensity at some point is that charge, rho sub s ds, divided by 4 pi epsilon sub 0 times the distance squared from that differential charge to the point we're trying to find the electric field intensity, times a unit vector pointing from the charge differential to the point where we want to find the electric field intensity. Then the total electric field intensity is just the integration of the contributions to the electric field intensity from all the charge along the two plates. But we don't know the charge density on our two plates, so we can't use this technique. We also used Gauss's law to find the electric field intensity, but Gauss's law also requires knowledge about the charge distribution, plus we have to be able to match a Gaussian surface to the symmetry of the field, which again we can't do for this situation. A third way we could find the electric field intensity is by taking minus the gradient of the electric potential field, but we don't know the electric potential field. Now, actually contained in Gauss's law, actually the point form of Gauss's law, and E equals minus the gradient of the potential, is how we're going to be able to determine the electric field intensity and the electric potential field when we have two conductors and we know the potential of each of the conductors. Here we have the point form of Gauss's law, and here the relationship between the electric flux density field and the electric field intensity using the absolute permittivity. So we're going to substitute for the electric flux density field in Gauss's law epsilon times the electric field intensity. To proceed, we have to make one assumption, and that assumption is that the absolute permittivity is not a function of position. In other words, the permittivity is a constant. Let's see what that means for us. So let's see how we can modify this equation if epsilon is not a function of position. First, our del operator in Cartesian coordinates looks like this, and it's going to be dotted with epsilon times the electric field intensity, and here we have the electric field intensity written in terms of its three components. So taking the dot product, we'll have ax dot ax is 1, so we'll have a partial with respect to x of epsilon times e sub x, and then ax dot ay is 0, ax dot az is 0. Move to the second term, ay dot ax is 0, ay dot ay is 1, so we'll have a partial with respect to y of epsilon times the electric field component in the y direction, and finally the same thing for our third term. With epsilon not being a function of position, we can move it to the left of the partials with respect to x, y, and z, and now we can rewrite this as epsilon times the divergence of the electric field intensity. So the condition of epsilon not being a function of position means that we can move it to the left of our divergence and rewrite this equation as epsilon times del dot the electric field intensity is equal to the volume charge density. So epsilon not being a function of position means we can move it to the left of our divergent operation and then divide both sides of this equation by the absolute permittivity. Now for the electric field intensity, we're going to substitute minus the gradient of the potential field, and then multiply both sides of this equation by minus 1. Now this operation of taking the divergence of the gradient of a scalar field is written as del squared V, and this operation of del squared, which is the divergence of the gradient of a potential field, is called the Laplacian. So this equation right here, that the Laplacian of the electric potential is equal to minus the volume charge density over the absolute permittivity, is referred to as Poisson's equation. And in situations where there's no volume charge density, so that we can rewrite Poisson's equation as the Laplacian of the electric potential equals to 0, is called Laplace's equation. Poisson's and Laplace's equations are second-order differential equations, and with knowing two boundary conditions, you can solve these equations for the electric potential field. Let's find the form of the Laplacian in Cartesian coordinates. So the Laplacian is the divergence of the gradient. So the divergence, we have the del operator in Cartesian coordinates, and we're going to take the dot product with the gradient of the potential, which is just the del operator times the potential. Okay, so this operation of the gradient gives us this form right here. And now when we take the dot product, ax dot ax is 1, so we'll have the partial with respect to x and the partial of v with respect to x, which is just the second derivative of v with respect to x squared. Then ax dot ay is 0, ax dot az is 0. Second term, ay dot ax is 0, ay dot ay is 1. So again, we'll then have the second derivative of the potential with respect to y now, and ay dot az is 0. Third term, az dot ax is 0, az dot ay is 0, az dot az is 1. So we're left with the second derivative of the potential with respect to z. So the Laplacian in Cartesian coordinates is given by this expression right here. To get the form of the Laplacian in cylindrical and spherical coordinates, you just apply the forms of taking the divergence and gradient in cylindrical and spherical coordinates to get these expressions for the Laplacian in cylindrical coordinates and the Laplacian in spherical coordinates.